尊敬的各位来宾，亲爱的朋友们，大家晚上好！欢迎来到2025年国际基础科学大会数学之夜的现场。My name is 山洪王 ，I'm from Southeast University.
Distinguished guests and dear friends, ladies and gentlemen, good evening. Welcome to the Mathematics Night of 2025 International Congress of Basic Sciences. My name is Gan Ziying from the School of Social Sciences in Tsinghua University. It's our honor to be the host of this great event.
今天我们齐聚北京，将在这里共同度过一个独属于数学的美妙夜晚。首先，请允许我介绍今天来到数学之夜的重要嘉宾。
Tonight, we are all gathered here in Beijing to spend a wonderful evening that belongs to mathematics. First, please allow us to introduce the distinguished guests joining us tonight.
他们是国际基础科学大会主席、数学之夜的主办方上海数学与交叉学科研究院理事长邱成桐先生。
ICBS Chair, Fields Medalist, winner of Wolf Prize, Shao Prize, Chairman of the Board of Shanghai Institute for Mathematics and Interdisciplinary Sciences, Professor Shin Tongyao.
德国海德堡科学院院士、美国数学会会士、德国图宾根大学教授 Gerhard Huisken.
Member of the Heidelberg Academy of Science, member of American Mathematical Society, Professor at the University of Tübingen, Gerhard Huisken.
2025基础科学终身成就奖得主，麻省理工学院教授 George Lustig.
Winner of Wolf Prize, Shao Prize 2025 Basic Science Lifetime Award, Professor at Massachusetts Institute of Technology, George Lustig.
菲尔兹奖2025基础科学终身成就奖得主，京都大学教授森崇文。
Fields Medalist 2025 Basic Science Lifetime Award, Professor at Kyoto University, Shigafumi Mori.
菲尔兹奖得主，美国国家科学院院士、中国科学院外籍院士安德烈·奥肯科夫。
Fields Medalist, member of the U.S. National Academy of Science, foreign member of Chinese Academy of Science, Andrei Okhenkov.
今晚在场的，随后会有演出的，还有菲尔兹奖得主、欧洲人文和自然科学院院士、英国皇家科学院院士 Coach 贝尔卡。
Fields Medalist, Academia European member, Fellow of the Royal Society, Culture Birkar.
菲尔兹奖得主、欧洲人文和自然科学院院士、洛桑联邦理工学院教授 Marina Wiercławska.
Fields Medalist, Academia European member, Professor at Swiss Federal Institute of Technology in Lausanne, Mariana S. Wiazowska.
ICM 演讲者，清华大学教授，求实杰出青年学者奖获得者单鹏。
ICM invited speaker, Professor at Tsinghua University, 求是 Outstanding Young Scholar Award, Peng Shan.
再次欢迎各位的到来。接下来就让我们开启第一个环节，有请两位教授进行主题演讲，分享他们最新的学术研究。首先有请 George Lustig.
Now let's start the first session. We'd like to invite two professors to give general lectures and share the latest academic research with us. First, let's welcome Professor George Lustig. The title of his talk is Strata in Reductive Groups. Welcome.
Okay, so this lecture will be about strata reductive groups, and I don't think everybody knows what is a reductive group. So the typical example of such a group is n Bayer matrices, invertible n Bayer matrices GLN over complex numbers or over algebraic closed field of characteristic P. So but what I will say, I will it will also apply to groups like special orthogonal group, like transformation in n-dimensional space. We preserve non-degenerate quadratic form and have determinant 1, and also applies to exceptional groups like this exceptional E8 over complex numbers. But in any case, I will state what we should do for GLN, and then, but results are mostly interesting for other groups. Okay, so let's start. So we denote by G0 reductive connected algebraic group over complex numbers, and you should think of that as GLN over n binary matrices over complex numbers. And then this reductive group has also some analogs over any algebraic closed field, and I want to take over algebraic closed field, algebraic closure of a finite field, Fp, and that I denote by Gp. So P is any prime number or zero. And actually the main thing I want to explain is how such a group can be decomposed into finitely many, it's a disjoint union of finitely many pieces. And I think this should be quite useful for various things. And I think it hasn't been, it's not something well known. Yeah, and one of the main properties of these pieces is that the indexing set for the pieces will be the same in any for G0 and for GP, so independent of P. And so now one definition. P is a variety of Borel subgroups of GP, and in our case if you think of GP as a automorphism of vector space and dimensional, then Borel subgroups will be BP will be the set of complete flags in this vector space. So sequence of subspaces of each dimension. Or you can say that BP is the set of conjugates of the upper triangular matrices. So that's algebraic variety. And now for every element in the group, GP, you can look at all such Borel subgroups, or these are conjugates of triangular matrices, which contain this element G. This is called the Springer fiber. So which means that you could think in GLN, you take a n by matrix, and you look at all complete flags which are stabilized by this element, and that's always a non-empty set. And there's a theorem of Spartenstein that all irreducible components of this variety have the same dimension. And let's call that D of G. Now, so now we can consider the homology group of this Springer fiber in dimension twice d of G. And you can map that to the homology in the same degree of the full of BP itself, because if BP of G is contained in BP, so there's a natural map from homology of one to the homology of the other, and IG is the image of this map. And then you can define equivalence relation on GP by saying the two elements are equivalent if this IG and IG prime are equal. So that's an equivalence relation. And the equivalence classes are called the strata of GP. And now there are some claims. Oh, by the way, I should say that if you are in classic P, you have to use homology. There's some étal. There's some notion of this appropriate homology groups in that case. So one claim is that each stratum is a union of GP conjugacy classes of fixed dimension. And then it's also true that each stratum is locally closed in GP. And this was proved by, I conjectured, it was proved by Carnovale. It's also true that there are finitely many strata. So this gives a decomposition of any group into finitely many strata. So in one example, this one example of such a stratum. It has been known, has been considered a long time ago by Steinberg. So there is a following stratum. You take all, it's called a regular stratum. They're all elements of GP, such that this number D of G is 0. So the set of Borel subgroups containing G has dimension 0. It's it's a finite set. So this is a stratum, and it's an open set in GP. Okay, so now now we consider what is called the Val group of GP. So in this case, if you have GLN, this will be the symmetric group in n letters. And in general, it is something independent of P. So this Val group, it is known that it acts naturally on each homology group of this BP, it's called a Flagg manifold. And now remember that we have defined for any element G in the group, we have defined something called IG. It was a subset of the homology of the full Flagg manifold, subspace. And in fact, you can show that it is an irreducible, so as a representation of W is irreducible. So this follows from work of Springer. At least in GLN, it's for any prime, but in other groups, for most primes with Springer, and I proved it for some remaining primes, for some small primes. Okay, so now, so in particular, we have a map from the set of strata corresponding to this P. P is a prime or 0, to the set of irreducible representation of Val group. And one can show that this map is, first of all, is injective. And this image you can call irreducible with the star of W is independent of P, of this prime or 0. So in particular, the set of strata is finite, and its indexing set is independent of P. So you can think of set of strata as a sigma without an index. It's just something attached to a group in which you don't specify the field. So now it has some. So now, what are connection of this strata with unipotent conjugate? I don't know how much time I have. When okay, so. So in GP you have a set of unipotent conjugacy classes. So if this was GLN, this would be all matrices which have all eigenvalues 1. But up to conjugacy. And this is a finite set. And there is some natural map from the set of unipotent classes to irreducible representation of our group, which is injective. And its image it can be denoted by irreducible representation with index P of W. And there's a theorem that this irreducible representation of W, which index the strata, is exactly the union of this set's irreducible P of W over all primes or 0. So this gives another reason why this set of strata is finite. So then you can interpret this equality. You can saying that the set of strata can be viewed as a union of the set of unipotent classes for various P. So this union, if you regard both sides as a subset of the set of irreducible representation, then this union is taken in that set. So for example, if you take if you take, there's a group, one of the most interesting groups in the world is group of type E8. So this is a group of dimension 248. And in this case, just to tell you what this strata look like, so there are 70 unipotent classes over complex numbers. If you take this group in classic 2, it will have 74 unipotent classes. And if you take this group in classic 3, it has 71. But the number of strata is actually 75. And how do you see that? So there's a set with so there are 70 classes in classic 0, and then you have to add 4 classes in classic 2, which are not in classic 0, and also 1 class in classic 3, and this form the set of strata. So now it turns out that every stratum contains at most one unipotent class, conjugacy class. But a stratum contains, actually does contain unipotent class in some characteristic. So if you change the characteristic, the so if you change the characteristic, the stratum will contain unipotent class. Of course, in GLN, this statement is trivial, but I state this interesting statement in other types. So, for example, here is an example. If you take a symplectic group In fact, I don't know, did I run out of time already or not? I don't know, what's the time? Anybody? I don't know how time, what's the time? Huh? 1 minute? Okay. Yeah, so in symplectic group, as before, there are 5 strata, and if characteristic is different from 2, then 4 strata contain unipotent class, and 1 stratum doesn't contain unipotent class. It is the class of this matrix 1 minus 1 minus 1, 1. But if characteristic is 2, then every stratum contains a unipotent class. And in GLN, any stratum contains a unique unipotent class. Okay, maybe that's it. So,
Thank the speaker very much. Any question or comments? Okay, here.
So, Professor, can you please provide some motivating examples as to why do we consider homologic groups of the Springer fiber?
no, what? Can you repeat?
So why the homologic groups of the Springer fiber has something to do with this stratification?
Well, just because it works, so it works. So this definition works. So why not use it if it works? Yes.
Okay, thanks a lot. Due to time constraints, we only just one question to ask. Thank you very much. Thanks.
Okay.
Now, let's welcome our second speaker, Professor Peng Shan. The title of her talk is Monoid Categorification of Skin Algebras. Thank you. Welcome.
Thank you very much. I'd like to thank the organizers for giving me this opportunity to speak at this great occasion. So I will talk about monoidal categorification of skein algebras, and this is based on joint work with Dylan Allegretti and Hyun-Kyun Kim. So maybe let me start by explaining what is a categorification. So roughly speaking, categorification of an object just means you have some higher structures which realize your object A as a shadow. So for example, take a finite dimensional vector space, and then you can take its dimension that gives you a number, and you can say this number is the shadow of this vector space. And then you have some more refined version of this where you take a graded vector space, which is just a direct sum of finite dimensional vector spaces, and then you can take the dimension by remembering the dimension of each of the pieces and then this gives you some Q number where Q is just a variable. So it gives you some Laurent polynomials in Q, which remembers the dimension of your graded vector space. So more generally, the word categorification comes from this notion of category, which is a mathematical structure consisting of objects and morphisms. And assume your category have some sort of exact structure. Say you have a Billian category with some short exact sequences. Then you can perform the construction of what is called a Grothendieck group. This produce out of your category a abelian group, which is just a free abelian group generated by the isomorphism classes of objects in your category. And then you mod out the relation where if you have an object which is an extension of two objects, you just say the class of this object is the sum of the two sub or quotient objects. So roughly speaking, this gives you a abelian category which only remembers the size of your objects in the category by ignoring other informations. And sometimes if you, so you can see that backwards saying that this category provides a categorification of this abelian group. And sometimes you want to do some linear algebra, so you want to have a vector space instead of a abelian group. So you can just complexify your Grothendieck group by changing the coefficient to complex numbers. This gives you a vector space. And if you want to do algebra, so what is an algebra? It's a vector space with a structure of multiplication. And then you can categorize them by putting a monoidal structure on your category. That is, you're allowed to multiply objects in your category. And then suppose it behaves well with these exact structures on your category, then it descends to the Grothendieck groups and give you a multiplication structure on this vector space, which produces you an algebra. So the thing to take back from this slide is basically a categorification of an algebra is provided by some monoidal categories. Now let's look back at our initial example. So what were we doing? You can consider the category of all vector spaces with morphism, just linear maps, and then take its Grothendieck group, and this produce you the trivial algebra, which is just C. And then you have tensor products of vector spaces, which gives you the multiplication on C. But you look at this, and there's something particular happening, that if you take a vector space, which is an object, its image in C is not some arbitrary thing. It must be a positive integer, right? The dimension of a vector space is positive. And you have something similar for the graded vector spaces. So more generally, if you have a monoidal abelian category with some suitable finiteness condition, and then you take its Grothendieck group, you have an algebra, then a basis of this vector space is spanned by the classes of simple objects in your category. And this basis have a positivity property in the sense that if you multiply the classes of two simple objects, you will get a linear combination of simple objects whose coefficient are positive numbers, positive integers. Why is that? Because if you do the convolution in your category, you still get an object in your category, which is built up from simple objects. So you descend to the Grothendieck group, this coefficient, which I wrote as aijk here, is just encoding how many times the simple objects appearing in that tensor product. Okay, and so why are we talking about this and what categorification is good for? There are two sources of motivations let's say. There's one, let me just say, there's one motivation from quantum topology. So when people study knot theory, we study knots in S3, and then we know that Jones polynomial is an important invariance for knots. And then Kovanov gives some categorification, produce some more refined invariance, which you can think of it as a categorification in the sense we just produced. So we just discussed, it's like a complex of vector spaces, and then if you take its dimension, it produces you some Jones polynomials. And then Jones polynomials generalized on one hand by Witten, Reshtikin, and Turayev. They construct invariance of 3 manifolds and constructed some 3D TQFT. And this is also a place where people are currently there are many works of categorification of this construction happening in the last, I don't know, for maybe 30 years or more than that. And so this is related, for example, to categorification of quantum groups. And this was first appeared in a proposal of Crane and Frankel. And then it was pursued, the constructions of categories was pursued in the work of many mathematicians like Kovanov, Lauda, Rugier, and many people that I don't have the space to cite here. For example, this morning, Vivek Shende just gave a very nice talk on how to use Fukaya categories to categorify things related to this. And then there's another direction to study invariance of 3 manifolds, which is called skein modules. And in particular, you can consider some skein algebras. This was introduced by Przybylski and Turayev in the 1991s. And then the categorification of which is the topic of my talk today. Okay. And on the other hand side, in representation theory, categorification also plays a very important role. So as Professor George Lusick mentioned in his talk yesterday, he constructed this categorification. Well, he didn't formulate in this terminology, but basically he constructed the categorification of the positive part of the quantum group using some sheaf categories, some derived category of constructible sheaves on representation of quivers. And there's a convolution structure on this category, which makes it monoidal. And then in this category, there are some very distinguished objects, which called intersection cohomology complexes, and their image in the Grothendieck group provides precisely this canonical basis. And this was the origin of this basis. And these bases have many important applications in representation theory. For example, they're extremely important for computing character formulas for symmetric groups over a field of characteristic P when P is large enough, and also for Hecke algebra as roots of unity. So there's some important work of Grotchinovsky and Ariki addressing this. And then the idea of categorification of Kac-Moody algebras was further developed by, for example, there's very important work of Chang and Rukie where they produce some refined notion of SL2 categorification and use it to prove an important conjecture of Bu-Hu-Wei on abelian defect group conjecture for representational finite groups. Okay. And so the categorification we're talking about today is roughly in this style. You use some kind of sheaf categories on variety to produce a categorification of your algebra. So the main result at a glance is the following. You take a genus zero curve with n plus 3 boundary components. So I denote that as 0, n plus 3. And then one can consider its skein algebra. And our results proves that there exists a monoidal category of equivariant causal perverse coherent sheaves. These are some complicated terminology, but basically some categories of sheaves on a space introduced by Braverman, Finkelberg, and Nakajima. And this produced a monoidal abelian categorification of the skein algebra. And in particular, you can consider the simple objects in this category provides a positive basis of the skein algebra. So the existence of a positive basis has been conjectured by Dylan Thurston in 2014 and has been studied by many people in many different ways. And so we provide a new categorification of this algebra. Okay, maybe let me give you more detail on the content of this theorem. So what is a skein algebra? So you take S to be an oriented surface of genus G and with n boundary components. And then you can consider the following space of, which is a free module over the ring of Laurent polynomials in A. So A here is a quantum parameter. You should think it's roughly Q before. And it is spanned by isotopy classes of framed links in the three manifold S cross an interval 0, 1. Okay. And then on this space, you can put an algebra structure just by superposition. So you have your surface cross the interval 0, 1, and then you can just stack it onto itself and take unions of all the links inside it. And then, so this forms an algebra. And what is the Kaufman-bracket skein algebra? This is the quotient of this algebra by the so-called skein relations, which is like locally, if you have a crossing like this, and then you just replace it by two ways of resolving it, either like this or like this, and then by putting some quantum parameters in front of it. And then if you just have a free loop, you can replace it by a squared plus a minus 2. Okay. And then an important result of Przyczynski and Turayev is that they prove this algebra, it quantizes the ring of regular functions on the character variety, which is the moduli space parametrizing principal SL2 bundles with flat connection on your surface S. Okay, and this can be described in very elementary terms. So by Riemann-Hilbert, it's just the space of group homomorphism from the fundamental group of your surface to SL2, and then you consider them modulo the conjugacy action of SL2 on the target. And if you specialize the parameter in the scaling algebra at A equals to -1, you obtain functions on this character variety. And then there's some relative version of this. It's like if you fix some curves around your boundary components, which I denote by delta 1 to delta n here, and some complex parameters lambda 1 to lambda n, and then you can make a quotient of the scaling algebra by specializing the value of this pre-loops delta I to be minus lambda I plus lambda I inverse. And this is a quotient of scaling algebra which quantize a closed scheme in the character variety, parametrizing those representations of the fundamental group whose value at this delta I are conjugate to this semi-simple matrix lambda I inverse. Okay, so this is the scaling algebra. And then I want to say a word about this Braverman-Finkelberg-Nakajima construction. So they give a mathematical construction of Coulomb branch for 3D n equals to 4 supersymmetric gauge theory. Their input is a reductive group acting on a vector space. And out of this, they produce a complicated infinite dimensional loop space whose definition I'm not giving here. But the important thing is on this space, you have an action of an arc group G of O, and then you can also rotate your loop, so you have a C star action. And then they consider the equivariant K theory on this space RGN. It is a sort of Sternberg variety, and you can perform convolution products on K theory. So this produces you an algebra, and what is remarkable in this case is the commutative algebra. And you can take its spectrum, it gives you a fine variety, and this is what they call Coulomb branch. And this construction naturally comes with a quantization. Is that if you turn on in the equivariant group the loop rotation equivariance, then this algebra is not commutative anymore, and it provides a quantization of the previous algebra. It also has natural deformations. So if on your vector space N with this G action, you have an additional group F acting, commuting with G, then you can also consider equivariant K theory by adding in equivariance for this group F, and this provides you a deformation of this BFN algebra. So our idea is to relate scaling algebra to this BFN algebra, this equivariant K theory. But you see immediately the inputs are very different. For scaling algebra, you started from a surface of genus 0, well, some surface, and then here the input is a group and a representation. So I need to tell you how do you assign the data of a group representation to the surface of genus 0 and n plus 3. So what you do is you consider this tube here is supposed to be a sphere with n plus 3 punctures on the boundary. And then I had the free loop delta i's. And I fixed the Pence decomposition by cutting it at the curves called gamma I. And then to this, I attach a quiver. For each gamma I have a gauge knot of the quiver, and the dimension is 2. So in the picture, I have n of them. And then I have 2 framing vertices at the end. And then I just consider representation of this quiver. So the group will be a product of gi with So gi is SL2, and then I have one SL2 for each of the orange vertices. And then I take the representation of this quiver, which is just the home space I'm writing here. So So some home space between vi plus 1, and each time vi is just the standard representation for the corresponding SL2. Okay, and then there's some commuting action with G, which is just a torus F. It acts on the framing vertices and also by scaling the edges. So yeah, so this construction was following some ideas of Gayotto in n equals 2 duality. And then the theorem we prove is that, so we can identify the coefficient range of the scaling algebra with the equivariant K theory of the C star rotation and this torus F equivariant K-theory of a point. And so here A is the quantum parameter corresponding to the Q in the C star rotation, and then the others are the parameters in the F equivariant K-theory of a point. Then there's the isomorphism of K algebras between the relative scaling algebra associated to the surface with n+3 punctures, and this BFN algebra, which is the equivariant K-theory, with the G, N, and F I explained above. Okay. So in particular, this is an isomorphism over the integral form, so you can specialize A2 - 1 and obtain an isomorphism between the character variety and the BFN Coulomb branch. And just to end, so this equivariant K-theory is by definition the Grothendieck group of the equivariant derived category of coherent sheaves on this space. And in this situation, Curtis and Willems defined a remarkable T structure on this category, which is called causal perverse coherent T structure. Its heart is a abelian category, which we call this PGN. It is a abelian category, and remarkably, it is closed under the convolution product. And so, therefore, as a corollary, we have a monoidal abelian category whose Grothendieck group is isomorphic to the scaling algebra, and therefore the simple modulus provides a positive basis. And just a final remark, so there are other people working on this subject. There are other people looking at scaling algebras, categorification of scaling algebras using a different approach, more similar to Kolanov homology. And for example, there are work by Asaida, Przybylski, Sikora, and Kefelak-Wedrich. Okay, and so here are my collaborators. Dylan is there in the audience, and then papers are available on arXiv. Thank you very much.
Thanks, speaker, very much. Any question? Okay, that guy.
Hello, professors. As shown on your slide, that the scaling algebra can be viewed as a deformation of ring of functions of the SO2 character variety. So I like to ask that, what makes the group SO2 so special here, or are there any similar stories for other groups? Thank you.
Yes, there are other scaling algebra associated to other reductive groups, but what makes SL2 special is this scaling algebra is more explicit. You can describe it in this, using this Kaufman scaling relations, and the others are more subtle to describe.
Okay, more question? Because we have more time. Okay, thanks, speaker.
Thank you.
Let's thank the speaker, all speakers again.
Thanks again for two professors and the participation of the audience. I believe the lectures have sparked a lot of thoughts among us all. This is exactly the significance of the Mathematics Night. As previous years, the International Congress of Basic Sciences this year has also awarded the Frontier Science Prizes with over 100 laureates in the field of mathematics. Next, we will invite 4 award representatives to share their insights on academic pursuit. First, let's welcome Professor Sergei Gukov from the California Institute of Technology, who is the professor of the mathematics and theoretical physics. Welcome to the stage.
Thank you very much. Ciprian, who is another author on the paper that was awarded this FSA award, and I are extremely honored and humbled to be selected for this award. We are very, very grateful to ICBS and FSA Selection Committee for choosing our work. I won't be able to tell you what the work is really about in detail, but it's actually on the same subject that Professor Peng Sheng just explained. It's bridging non-commutative algebra and low-dimensional topology. But I want to tell you a little bit about the style of the work and what it feels to work in this field. In particular, hopefully these remarks could be helpful to young scientists. In general, in my research career, which has been over 20 years, I love building bridges, not just between different areas of mathematics, but between mathematics and other fields, such as physics and string theory in the past, and computer science and mathematics more recently. And hopefully one day I'll be back to Beijing for FSA in information science. So this areas of kind of interfaces between different sciences are extremely fruitful, and there is a lot of bread on a table that's often left at these junctions between different fields, different areas. And this has come up already in a number of speeches, for example, in Professor George Lustig's acceptance speech, and even the talk by Peng Chang that you witnessed a moment ago is also bridging several different areas. So I definitely advise young scientists to go there, but I also want to highlight a couple of aspects which make it fun and interesting. So first, someone could object, hey, Sergey, doesn't it require expertise in two different domains to build a meaningful bridge between two different areas? And some of the students already expressed concerns that we have a growing body of information that they need to learn. And you would be absolutely right that, yes, it is true that it requires expertise in two different domains. And now that I work on computer science and AI and mathematical reasoning, I sometimes see computer scientists who try to build models of mathematical reasoning by having only idea of what International Math Olympiad is about. And of course, that's very far from research level mathematics. And to be fair, conversely, I sometimes see colleagues in mathematics who think that they can master AI techniques in a couple of months, and that's also not true. So it does require a whole PhD in each subject to build enough expertise to say roughly at the level of being able to give a graded course in each given subject. So yes, it takes additional effort, and it is extremely important. I'm not advising to be total novice and trying to build this bridge, so it does require additional effort. But good news is that this is pretty much the only bad news. So yes, it does take additional time to build this expertise, but then there are lots of benefits. First, it's fun to learn new things. It's just easy to explore these new areas, and earning PhD takes only about a couple of years, 3 or 5 years. And once you repeat the process, of course, you don't have to waste time on the same calculus class or basic topology class. So basic classes, of course, serve as foundation for many different subjects. Another benefit of working at the interface of different fields and building these bridges is that people love explaining what they did and discovered. So I was very lucky to receive mentorship from many different people, amazing people in many different areas. Many of them are in fact in the audience, and I'm very, very grateful to them. I was a postdoc of Professor Yao, and together 20 years ago, we were studying geometry of G2 Halon manifolds. I learned quantum topology for Kolya Reshetikhin, who is sitting here in the audience. And if you go and try to build bridges, you'll basically receive many different mentors from different fields, which is a lot of fun. And also, last but not least, this is a great way to build a community of new friends. So by trying to build bridges, you'll acquire more and more friends. So I want to finish these thoughts by also pointing out that recently, together with Professor Yao and team in Tsinghua, we built another bridge. We built a collaboration between Caltech and Tsinghua University at all vertically integrated levels, meaning students, postdocs, and faculty. And if any of you are interested in being part of it, please ask me questions or Professor Yao questions. And again, thank you to BIMSA, thank you to ICBS, and thank you to FSA Selection Committee. It's a great honor.
Thank you for Professor Sergei Gukov. Next, let's welcome Masahito Yamazaki from the Kavli Institute for the Physics and Mathematics of the Universe, University of Tokyo, to deliver his acceptance speech. Welcome.
So thank you, everybody. So it's a great pleasure and honor for me to attend this ICBS event. So this is my second event, second time to participate in this event. And it's an amazing event, and I really hope that we will continue. Also, I'm very humbled to receive the Fundamental Science Award. And I'm not going to explain the content of the paper. It's about the relation between mathematics and physics, how to try to understand integral models and mathematical structure they're in from some quantum field theory. But let me try to share one small anecdote, which actually has a lot to do with China. So I started that collaboration when I came back to Institute for Advanced Study in 2016. In April 2016, I have been working on integral models, and Professor Edward Witten, who was a host there, was very excited about the integral models back then. I could visibly see that. And we started talking, and then we also joined forces with Kevin Costello, who is at Perimeter Institute. And it took some time, and then we made our first announcement of the results in 2016. In fact, right in Beijing. Of course, there was no BIMSA, but at Tsinghua University, there was a conference called the Strings 2016 conference. So I'm very pleased to hear that the Strings conference will be held in Shanghai next year, 2026, 10 years after. And but anyway, our first announcement was at the Tsinghua University at 2016. And afterwards, of course, the basic story is there. We started working out things. But then the draft became longer, and we attempted to fill in the gaps in many places. But then there was actually, at some point, I encountered some difficulty. I was doing some computations, and I should get a factor of 5, but instead I was getting 2. And it was actually, no, I was supposed to getting 2, but I was getting 5. And I was very perplexed. And then I literally spent more than months trying to figure out the factors. And that should work out that way. But eventually, I managed to work out the factors correct. And the theory was completed. And we published the papers in 2 papers. One in 2017, and one in 2018. Now, well, of course, that's published in arXiv, and then we have to send it to a journal. And Professor Edward Witten suggested us to send a paper to the journal called Notices of ICCM. So it's a notices for International Consortium for Chinese Mathematicians. And so I'm very pleased to see that our 2 papers are published in one of the volumes there. And in fact, I noticed that it's actually published alongside with a foreword by Professor Yao on the opening of the ICCM. And there was even an article by Professor Stephen Hawking and Gordon Kane on the future of collider physics and collider physics in China. So I'm very pleased to see our paper getting published there. And so somehow the story has a lot to do with the events in China. So maybe it's not a complete coincidence that I'm coming back here to accept the award awarded from ICBS. Now, over the years, I have been very impressed by the commitment of the China as a country and as a society for the general educations and also the research in mathematics and physics and fundamental science in general. And I'm very pleased to see that, especially in view of what's happening in many different parts of the world. And it's really amazing to see that because indeed mathematics is one of the common languages we can communicate. So once Galileo said that mathematics is a language to describe the world. And in fact, mathematics is really a common language where people with the different backgrounds, cultures, can communicate effectively. And that's that's very much a pleasure for me. Sometimes I run into somebody whom I never met before, but then I can strike a conversation about a particular theorem instantly. And that's the beauty of the mathematics. And I'm very pleased to see that such spirit is well represented by the events of this conference. Thank you very much.
Thank you for Professor Yamazaki. Now let's welcome the last speaker, Professor Chen Gao from the Center for Geometry and Physics of the University of Science and Technology of China. He will share his mental journey from the young talent to where he is today. Welcome.
Good evening, everyone. It's my great pleasure to attend this wonderful conference, to receive the Frontiers of Science Award, and to speak at today's Math Night. My paper studies the J equation and the deformed emission Yang-Mills equation. As mentioned by the previous speakers, my paper also built a new bridge between differential forms in differential geometry and subvarieties in algebraic geometry. This is kind of generalized Monge-Ampere equation. This kind of work goes back to Professor Yao's solution to the Calabi conjecture using the Monge-Ampere equation. I feel very lucky to contribute to this field and also to receive this award. However, honestly speaking, I was not always so lucky. For example, in ICCM 2022, I proposed a route map towards the Hodge conjecture, a famous open problem concerning the connection between differential forms and subvarieties. And however, even though I worked it for several years, the progress has been slow. Fortunately, with the encouragement from Professor Yao and my advisor Xiuxiong Chen and many others, I still keep enthusiastic on this challenging problem. There are many young audience in this room, so I'd like to share some of my feelings to you. The first thing I want to say is that try to dream big. For example, you can dream to be a top expert in your field. Dream for one of the interesting problems in your field, or you can try to go for the 7 Millennium Prize problems, for example. Second, every big dream starts small. So please start with simple problem first. Even though most of your attempts may fail, any minor improvement matters. It will help you build up the confidence and the skills to go further. Third, try to learn from classical papers in your field. For example, when I was around 20 years old, I studied many breakthrough papers in my field, written by Professor Yao, Professor Donaldson, and other mathematicians. From these works, I didn't see any magic tricks. Instead, I see the hard work, the patience, and the final success. I think this put a big impact on me. Fourth, try to learn from your peers. For example, at this ICBS conference, there are many wonderful talks. By attending them, you can keep your mind fresh, and it may provide some ideas for your own research. Finally, you are among the top students in China, and you are now in a good environment. I truly believe that you will achieve great things in the future. Good luck, and thank all the audience.
Thanks for Professor Chen Gao, and thanks for all the awardees for your sincere sharing, which has allowed us to experience more of the depth and beauty of mathematics. Now the first half of Mathematics Night has finished. About 1 hour later, at 7 o'clock p.m., we will invite 7 mathematics experts for a panel discussion. Now please move to the house B and C for the buffet. You can get the buffet tickets at the reception desk, or you can also move to A4 for dinner, which doesn't need tickets. See you later, enjoying the buffet. Hello everyone, welcome to the Mathematics Night of the 2025 International Congress of Basic Sciences. It is mathematics that brings us together. Before the panel discussion, first let's welcome Liu Ziang from Children's College in Tsinghua University. He will perform a piano solo, Chopin's Waltz in A-flat major, Opus 42. Composed in 1840, this piece is regarded as the most outstanding work among Chopin's waltz. Accompanied by the rhythmic patterns of a waltz, the music creates many thematic melodies with distinct characters, just like a bunch of colorful flowers. Now we will leave the stage to Liu Ziang. Welcome. Thank you, Zhang, for your brilliant performance. Next, let's welcome Chairman of the ICBS, Director of the Shanghai Institute for Mathematical Sciences, and the organizer of Mathematics Night, Professor Shen Tong Yao, to the stage to deliver a speech. Welcome.
Well, this is the third year of the ICBS being held in Huaiyou. I must say that each year I find it exciting to see new faces, old problems were solved, and new branch of mathematics has been developed. Many of them were influenced by the new subject that we have been interacting with physics, engineering, and many different fields. It's extremely healthy to see such a development that is happening, and we are organizing it together so our mathematicians can meet these great physicists that we saw in the last few days, and also the great engineers. And I think many of these new subjects has changed our view about things. Even some very abstract subject that I knew long ago, like category theory. When I was a boy, we were told category theory is a greatest subject. And then after a few years, nobody wants to look into the subject. Things that is abstract nonsense and useless. But in the last 10 years, we saw great development in category theory to the extent that I could not imagine that I would have thought about 60 years ago. My friends in condensed matter wrote me a long letters, told me how important the whole subject of category theory is in condensed matter. So things can change to a better way when we face new directions, new horizon comes up. Of course, we saw category theory already appears in Fukaya category and many other subjects in mathematics, but I was rather amazed to see that it appears in condensed matter. And the subject of computer science has driven many important subjects that was not so important to be considered in the old days, like combinatorics, now has become a very fundamental subject in mathematics, and many people are working on it. Probability theory, all these become one of the mainstream in mathematics nowadays. And I'm very excited to say that mathematics is very fresh and new, and is still asking for new important questions while we answer old questions. That's how mathematics develops. We have new concepts brought in, new foundation was built, and then we solve old problems at the same time, creating new interesting problems that can change the world. The subject that I helped to create, geometric analysis, I'm amazed to see many of our young friends are doing something that I envy about that they can do. And many of these things I would have thought about long ago. I didn't know how to do it. They were able to solve it, and they're leading to new directions and solving many important old classical problems in geometry. So I think this happens in many different subjects in mathematics, and it's very healthy. And this really makes us to think the International Congress of Basic Science merging three different important branch of science, basic science together is important, and that is healthy, that we would like to continue this conference for a long time. Thank you.
Thank you for Professor Yao. Please be seated on the stage for the following panel discussion. As the foundation of exploring the world, mathematics connects the abstract and the real. The path of advancing forward relies on the joint efforts of Mr. Yao, as well as all the mathematicians, professors, and young scholars present here. What difficulties and obstacles lie on the road of exploration? What are the latest perspectives on cutting-edge issues? Taking these questions with us, next, we will invite the 7 mathematicians joining us to start the session of panel discussion. First, let's welcome the host of the panel discussion, Professor Gerhard Huisking from University of Tübingen. Professor Huisking is a member of the Heidelberg Academy of Science and also a member of the American Mathematical Society. Welcome, Professor. Please be seated on the stage. Next, let's welcome Professor Shan Peng from Tsinghua University to the stage. Welcome, Professor. Please be seated on the stage. Next, let's welcome Professor Andrei Okhankov. Professor Okhankov was awarded the Fields Medal in 2006. He is a member of the National Academy of Sciences and a foreign member of the Chinese Academy of Sciences. His work spans multiple fields of mathematics, and he has achieved success in taking results from one area and applying them to seemingly very different ones. Welcome, Professor. Next up is another familiar face at Mathematics Night and also the winner of this year's Basic Sciences Lifetime Achievement Award, Professor Shigefumi Mori from the University of Kyoto. Professor Mori was awarded the Fields Medal in 1990. He established the framework of the Minimal Model Program, also known as the Mori Program. Welcome, Professor. Please be seated on the stage. Our next participant is Professor Mariana S. Biazowska. She was awarded the Fields Medal in 2022 for her profound contributions that connect number theory to classical problems in geometry and Fourier analysis. Welcome, Professor. Please be seated on the stage. Finally, let's welcome the winner of the 2025 Basic Science Lifetime Achievement Award, Professor George Lustig from the Massachusetts Institute of Technology. He is regarded as one of the greatest mathematicians of our time, having made fundamental contributions to algebra, algebraic geometry, and representative theory. Welcome, Professor. Once again, a warm welcome to all our distinguished professors. We eagerly anticipate your profound insights and brilliant ideas. Now let's hand over the floor to Professor Gerhard Huisking to host the session. Over to you, Professor.
Thank you very much, and good evening. Thank you for coming. I see a lot of young people in the room who already had a chance now for 4 days to listen to exciting lectures in a huge range of scientific subjects, from theoretical mathematics to physics to computer science. And I'm sure they are excited about many of them. But at some stage in their studies, they have to choose. And they have to find a balance between finding deep studies, deep insights in one area and acquiring broader knowledge. Do you have some advice for the young people how to make these choices and find this balance between deep insights and acquiring broader knowledge? I know this is individual. Maybe you can talk from your personal experience. Maybe begin with, at the end.
Yeah, I think it's a very important question. Personally, I think when I have some idea of what I'm going to think about and work on, I tend to try to focus. But at other occasions, I like to attend this kind of activities and listening to ideas from other people's.
Oh, we all take turn in answering this question. So I think there's a saying that nothing in biology makes sense except in the light of evolution. And I think the same applies to the scientific community. I think people just try different ways to balance this. Some people try to do it broadly, some people try to do it narrowly. Some people have success, some people have failure. And there's nothing wrong with pursuing your own path. You're finding your own balance. It's just you follow your own strategy in doing this. I think it's I think it's a general advice for me in mathematics. Do the mathematics the way that comes to you naturally. Don't try to force yourself into doing something which you don't find natural.
Yeah, I agree with what he said. So, for example, I like to I like to do whatever is most beautiful and not what is more useful so my first motivation is the beauty of something. Yeah. So, and I think that's what I recommend everybody to do. So, yes.
Well, I like to set up a goal that I like to understand the mystery of geometry, its beauty, and how they interact with other fields. That was always my goal. But in the process of reaching this goal, I explore many different areas that help me to reach such a goal. I read many papers in the library. I went to listen to many lectures that I can manage to do. Even when I was a graduate student, I listened to lectures given by physicists and engineers. Maybe that's my reason I formed this ICPS, both physics and engineers. I found that inspiring to listen to these people, to learn the problem that they want to solve. Many of these turns out to be very important for my own subject that I've been trying to develop in geometry. And I listen to people who can provide important tools. In those days, practically no geometer interested in analysis, solving differential equations. I remember many of my friends in geometry said that differential equation is a subject for engineers. We don't care about engineers. So I do not take that kind of view. I work with them and I learn how to use equations to build up structures. And it takes a long time to learn, and this turns out to be useful. Basically, I will just look at the problems in the most natural manner. When there's interesting idea come, I make use of them. If not, I try to create some ideas until I got stuck and just froze in that way. I work on many problems at the same time, so it's never lack of problem. When I got stuck, I work on another problem and come back again. And I never forget a problem that are interest to me. So for some problem, I work on it for 10 years before I got some good idea. And I have many good friends who help me to work out those problems. So we have many co-authors, and it's always rewarding to talk with them. So I encourage our students to do the similar thing.
Well, I do not have a straight answer. I agree that knowledge in some other fields can stimulate you. But in my case, things never happen that way. So as I mentioned in my talk, my main contribution was on the minimal model program. But originally, I was not particularly interested in. I learned it from Artem, but not actively interested. And I was more interested in a special problem called Hartson's conjecture. But even that, I found the proof out of a mistake. When I made a mistake, I found it myself. That's the only part I'm proud of. And I tried to understand what was happening, and I found the bend and break argument. And then I looked around, and turned out that it can be applied to minimal model program. So, like Stephen Chu mentioned last night, science doesn't proceed as carefully planned. Yeah, sorry.
No.
Yes, maybe I can add to this. As probably everyone's path of learning science is unique, and there is no universal advice that works for everyone. So maybe I can tell you how what works for me, how I think. So usually there are some problems or some questions that I think about right now that I would like to understand. And then whatever scientific talk I go to, I usually think, okay, so how is it related to these questions I'm thinking about? And usually if I find that it's not related in any way, then I probably often just lose interest and start doodling in my notes. But most of the time I can find some, maybe not a direct, but a philosophical connection. And this is how I find new interesting areas to learn for myself.
I guess this happens to all of us, that we often lose interest in something, or we get stuck, and then we go somewhere else. Did you have some situations where you really felt I made a major change in direction? I really moved from one field to the other, or I made a U-turn maybe even? Did that happen? An example? Yeah, George?
So actually, there's certainly a case for me. I think I did change. I did change from one field to another. So I was, as I mentioned, so I was a topologist in the beginning, and then after 2 years I became a representation theory person, but using the tools of topology. So it's very useful to mix two different fields. But I certainly changed completely from one field to another. Yes.
This was mentioned several times, that some of the most exciting developments in mathematics happen when different fields touch each other. Maybe there are other examples where other members of the panel made this experience, that they brought different fields together.
You know, when did my thesis, it was on using group theory to solve some problem in geometry. I did not think group theory is too deep at that point, so I left the field. But in many other fields, I never gave up. I always come back to the original field. So after 3 years, I graduated from Berkeley. I start to look into general relativity by listening to a big lecture given by Robert Garros, a physicist in Stanford University. I was very much hooked up by this problem, and I never gave up to think about that problem. And it took a long time until 4 years later, I solved that with my friend Rick Sher together. But it's on the course of we are looking at some other problem that we found the idea. So because I remember this problem, so during the course of studying other problem, we found the idea. And this happened to me many, many times because I'm working in 2 or 3 different subjects at the same time. one subject could get some good idea, help me to solve the other problem. Well, when I worked on string theory, it was much more tough because most of the concepts in quantum field theory was tough for me. So I still do not understand well, but I went to seminars in physics department every week in order to try to get to understand the language that they use. And that was not easy, but managed to help me a lot by just listening to them week by week, and then manage to talk with them. So I think it's very rewarding in all these years. Although I do not think I contribute that much, but still makes non-trivial contribution. It's useful.
You mentioned how physics influences mathematics, how physics poses problems, exciting problems for mathematicians. In which other fields do you believe that there's a major problems posed by other sciences that are exciting for mathematicians to solve?
There are many other subjects are really interesting, including in technology, computer science. There are many interesting problems. My friend Chong come to see me about 30 years ago to work on graph theory in application to computer science. And I just found it's fun to look at all these problems. So we started to develop something. And the last 20 years, we, with other people, we have developed quite a systematic research in graph theory. And turns out they are useful for many applied subjects, including medical science. So I found it fascinating. In almost any interesting subject with which you need to use reasoning, mathematics can play an important role.
Someone else maybe have an example? Or you mentioned computer science. I mean, of course, in computer science, I saw during the last 3 days, I saw many lectures that combine machine learning with traditional methods from mathematics to make huge progress. Do you have personal experience that in your work sometimes machine learning became essential or became just a tool, or you did not yet have to use it? Maybe you start.
It hasn't happened for me yet.
Okay.
Maybe I think it's somehow the understanding why machine learning works so well. I think this is one of the mysteries of our time, and also maybe more to your previous question, like what kind of things should motivate us, what we should understand. This seems to be somehow homework for mathematicians.
Yeah. Maybe it's even exciting homework.
Well, I feel the same way. Machine language is a mystery to me. I mean, just putting layers and adjusting the values, somehow it works. That I don't understand. And even if you get a very good answer, one cannot explain how the machine language gets the solution. And as a mathematician, I want to understand why. Yeah, until then, I'll be refrained from using it that much.
It's my impression that in some areas of science there is a danger that because of all these wonderful methods in machine learning, these methods are used without keeping the connection to basic physical principles that lie behind the phenomena. Do you share this view, or is this, am I too pessimistic in this?
Well, I think that a great deal of mathematics are needed to work into machine learning to make it to be a sound and good subject. And many of them are very fundamental mathematics that we know for years, but that not has been used. When I look at what the AI people do, they are using billions and trillions even parameters to solve the problem. That amazed me, that a problem needs that many parameters. And my conclusion is that the subject has been based on linear programming and linear methods. Too linear, that's why they need that many parameters. So I think people who work on nonlinear analysis, nonlinear differential equations should involve and clean up many of these problems and becomes much more tractable. So I think there are many rooms for us to get into the subject and do serious contributions. That's my view.
Given that you think it is so important, do you feel it has to be integrated somehow into studies at the bachelor level, at the graduate level? Do we have to change our teaching? Do we have to teach our students how to use AI prudently?
My view is that it is great that we get involved to improve and to understand the machine learning or the AI in a fundamental way. But it's a big danger that if all the students are involved in machine learning, in AI, they do not think more anymore.
Okay.
And that's the major trouble that I see it may happen.
I see some nodding there on the other end of the panel. Yes.
No, I was going to say about something else. It's and this will be also coming from me. Computer computation, symbolic, numeric, they played a huge role in what I did. But I want to bring an example from. So Ina and I, we have two physicists' daughter. Our older daughter, she works in computational GR. Subject must be very dear to Professor Yao Hart. Einstein's equations. Very, very beautiful equations, very difficult to solve numerically because of diffeomorphism invariance and other things. And of course, what they do, they have this amazing, really amazing numerical ways to solve it exactly. And then these are computationally extremely expensive, takes maybe months on a supercomputer to run, but they're good fundamental solutions, and from them they can machine learn, kind of other regimes. And what I advise people to do based on what I'm saying is that do not forget the good old numerical and symbolic computations in the process of converting to machine learning. Machine learning is a very helpful thing, but there's mathematicians, pure applied physicists, they've generated a real treasure of either good symbolical or numerical methods, which you shouldn't forget. You shouldn't. In my opinion, of course, like I said at the beginning, you all free to make your own decisions, and and see if they lead to failure or success. But my advice would be to keep studying, to keep learning also the good old things to solve mathematical problems. Not just start with machine learning.
Maybe if I may add, so there is a slogan I learned from my colleague computer scientist. So before think, then compute. And I think now when we have all this huge computational power that also comes at this very big environmental cost, it seems like a very good slogan. So first we think, and then we use all these amazing tools that we have now, and we compute.
Some colleagues, even in theoretical mathematics, like Peter Scholze or Terence Tao, they have used proof verification programs like Lean to check some very technical computations. And I remember Terry Tao even had this vision that at some stage maybe these proof checking algorithms become so fast that one can interact with them in order to find proofs. Do you have any view on that? George? You?
Well, again, yeah, so I only thing I can say about these computers, I know one thing, which is that like 50 years ago, I was at Institute for Advanced Study, and Borel was saying that, well, we are interested in Lie groups, which can be classical Lie groups or exceptional Lie groups. And Borel was always saying that where we can deal with classical groups, but exceptional groups are extremely difficult. That's a real challenge. But nowadays, the opposite is true. because of computers, you can check various things for exceptional groups first, and that gives you some idea for what happens in classical groups. So the total reversal. So that's something I think is remarkable. Yes.
Maybe I can share some of my experience of using Lean. So, yes. I'm currently working on the project where I try to formalize some of my results, and so maybe I can share what I somehow found out. So first, somehow learning Lean is not that easy, and even installing it on my computer was very uneasy. And also, I think we're still quite far from the moment when computer will start discovering like serious. Of course, it can, like, if you do search, you always can discover something, but I think at this moment it still seems to me we have a few more years of doing mathematics. Yeah, but at the same time, maybe there are like two different sides to what you said. Like, one is to, if you have a result, so should we try to formalize it? And here, maybe I would say that yes, maybe that's a good thing. So imagine that maybe some of you who are, so we have had a situation that you write some lemma and you publish it, and then sometime later somebody asks you a question about it, and you realize, oh no, this lemma is wrong. So it would be nice if, while we are latticing our proofs, we could also on the side formalize them, and then to make sure, okay, so at least I don't embarrass myself.
Andrew?
I think in my mind, the best application of Lean is an instruction. If teaching, like a teacher, the first proof-based class, it's sometimes hard to explain to students why something is not a mathematical argument, why this doesn't hold water. But if they just have to write something that either compiles or doesn't compile, that they have this kind of objective feedback. And so I think for many students, I don't know, I'm speaking in American context, proof is a complicated concept to grasp and to learn it against a kind of a very unyielding component such as Lean. I think it's actually very good, I think, in terms of classroom experience.
Right, but now you sort of, I think these answers sound slightly different. When I asked whether we have to incorporate it into the teaching of our students, you sort of said, no, they should not do too much of it, but there are some areas where it is important that they learn how to use this kind of new tools, right?
Say they shouldn't do something, they should, by all means, they should do everything. But I'm just saying, if you many American institutions to teach the first kind of rigorous math proof class you've never seen proof before, it's a challenge. You have to explain, somehow you have to explain why something is a correct proof or something isn't. And the easiest thing to have, just write it in Lean. It either compiles or it doesn't compile.
Maybe just a thing I personally ask about whether students should use AI, but they already use it. So it's not that we have control over it. And maybe another thing, if it lives in my mind, like this formalized mathematics and AI, they are somehow indifferent. It's like very different things. Of course, everything can be combined together, but those are like things like two very different questions.
I'm not quite following the argument, but this whole thing reminds me of my experience, bad experience with word processors. So I used to be able to write Chinese characters pretty well, but after using word processor, I cannot anymore. I think we are talking about the same kind of effect on the computer.
Yeah.
I think AI could be helpful to train many mathematicians who just work for routine mathematics development or engineer type things. But in order to make mathematics to really advance in the next stage, we need some creativity. And for that, we need a lot of curiosity, which largely depends on the taste of a person. Each mathematician has their own taste. I'm not sure whether AI could train some people who have some special taste. For example, George yesterday mentioned that he thinks that the greatest paper in mankind is Killing's paper on the Lie algebra. I think many of us may not agree. Some people may think Riemann's great paper was the greatest, and some people may think differently. So these are matter of taste and curiosity are built according to your own bias or your own taste. And I think AI probably would not be able to do that. It's a largely personality driven and your environment, how you were raised from.
I think this audience will all agree that we are fascinated about mathematics and we love the curiosity of looking at new problems. You seem to have been very successful in convincing larger part of society here in China to support this curiosity. It's not true in all countries. So what should we do to install this curiosity amongst the young people? There are some studies that you have to start even below 12 years to install this curiosity in science and mathematics in young people. Do we do enough? Or can we do more?
Well, in China, we train a lot of people who are skilled engineers. And that's one of the reasons I believe that engineer and industry are doing very well in the last 10 years. We have many skilled laborers compared with America or Germany or some other countries. So they are very important that we need to train these people. But in order to lead a major breakthrough in technology or in science, we need a smaller group of people who are willing to spend time to look at things fundamental and may not look useful. So my view is that we just need, say, in the order of 1% of students be trained in a more non-standard way. And this may not be trained by people with AI background.
Mm-hmm. So there's some experiences from other countries about how to train young people. I know there's a great tradition in Ukraine, for example.
Just I think that somehow many people have natural love for science and mathematics. I think it's just something we can learn very intuitively as children. So I remember when my son was very small, and at some point he realized that like 2 plus 3 is the same as 3 plus 2, and this was such an amazing happiness on his face. And I think he actually got it just intuitively. And so I think that maybe as adults, our job is not to kill this spark, but to nourish it, to not to make school boring, to support children. So in my own childhood, I remember what was somehow a big motivator for me. These were math competitions.
Okay.
This was somehow something I enjoyed a lot as a school student. I know that for some people don't like this kind of events. For some people, it does not work. For example, again, like my son didn't like things like that at all. But he still enjoys like science and physics and mathematics in other ways. So yes, so maybe it's not a very precise advice, and it's not clear how to turn it into a policy, but yeah, maybe it's more like a naive human one.
So I would say that everyday teaching is fine, but they want some small success. Building up a success above another, that may reach to bigger success. And when I was small, I used to be not doing anything much, but one small success experience. The teacher gave us a quiz, and if I got the quiz right, one can get a roll cake, you know. So how many people can get it? Well, they can cut it into equal pieces. And it was only that moment I got curiosity or appetite. I got it, and I was the only one. And that small success feeling remained for some time. Yeah.
Yes, actually, I was just thinking on the stage that whether, you know, AI or when we know many things, does that help to develop our curiosity? Because sometimes I feel I become more curious about something when I have becoming more familiar with it, or I have think about it for a long time, and then I have more question about it, which wouldn't arise at the first place. So yeah, maybe sometimes spending more times on something you're interested in would already help to develop some curiosity.
Professor Mori mentioned the importance of a teacher in this role in bringing the curiosity. Professor Yao said there should be just a small percentage who get sort of exquisite training. In some other, but don't we need also some understanding and sympathy for mathematics in a broader part of society in order to ensure that the broader part of society is supporting mathematics?
For some country like China, each year we have 14 million students graduate from high school. There are enough students who can work for the society. If we just choose 10,000 billion students to work on something more pioneering, more curiosity-based, which may lead to nothing, but it may lead to something, who knows? I think this certainly we can afford it for such a small number of people. And the way that is being structured is that everybody will take the same examinations. Everybody will be trained into doing the same problem in a certain manner. In the examination, sometimes you are not allowed to use different ways to solve the problem. And the examiner would insist that you solve some problem in some way. Not like in the old days when Gauss want to construct the 17th regular gun, use 17 methods, and each of them could be interesting and useful. And this is, I think, is not dynamical. I think we should allow in the order of, say, in the case of China, in the order of 10,000 students who are allowed to roam around in their way of thinking and give them basic training, and yes, should be able to create and go to many different fields. I think certainly we can afford it. There's no contradiction to have a large number of people just working in a routine manner. It's fine. Well, I mean, my son, for example, is actually very creative in biology. But when I try to teach them mathematics, he doesn't care too much. He just thinks in a routine manner. He was good in that, but not excited by the subject of mathematics. For this kind of students, they could go to different fields. maybe even in business, in law, in different subjects. It's fine.
No.
No, I don't. I can't say. I can't say how things should be, but I can maybe tell you sort of something I would consider to be a dream. And I think a very important, very important mathematics is not what we, what's the problem we consider or what's the conclusion we draw, but how we approach the problem. What we consider to be the input to the mathematical problem, what we consider to be the output. And this is to take the right point of view is sometimes much more important than to do any kind of technical manipulation. And I would, in some dream world, we would communicate that knowledge to much broader audience than it's currently communicated. And specific example, this is really coming from the heart. And so people, whatever kind of three-dimensional engineering you're doing whatever, quantum mechanics, you're doing electricity and magnetism, something, you will see the good old spherical harmonics, Legendre polynomials. And as a representation theorist, I must tell you, every time I see how this is handled by engineers, I just cry. And so if we could somehow communicate to people who really need these functions, how you think about them, and there are many such examples, that would be great.
And maybe as we are sharing dreams, so maybe I have another dream, is if everyone who goes to school and studies mathematics actually learns what is the concept of mathematical proof. Not in a sense that people should try to prove Riemann hypothesis, but just to understand what proof means. And actually we have a great way how to do it, right? So all this, like the geometry written by Euclid, it still exists. And it's, when I went to school, we studied this at school, so it's possible to do this at school. And I think this was a tradition which at some point got somehow lost or forgotten. At least I don't see somehow it, when I look at my son's homework, I see that. And I think this is something which many people could understand and enjoy, and this probably even could make our society a bit better.
I agree with you. I mean, my dream for Germany would be that in each high school there is one teacher who has the ability to really understand some mathematics and bring it to the most gifted students of his high school. That would be one dream. Maybe we share our dreams.
So I think everybody is different, and somehow, in my case, I'm interested in things which other people don't get. So just following my curiosity, I have been doing a problem which later people got interested in somehow, not the other way around. And it has been this way for more than 70 years, so I cannot change.
So you mentioned how important to have a good teacher in a school. So I disagree with that. At least in my case, when I went to high school, I think my parents sent me to the worst high school in town because that was only school where I had a chance to enter, because there were some, at that time there were things, you have to be working class or something in order to enter high school. So anyways, and this high school, the mathematics teacher was terrible, just terrible, knew nothing. And it was very good for me because I decided to study from using some mathematics magazine. So I spent all my time studying by myself, and I think it was much better for me. Yes.
But maybe this is just the best medicine for George Lustig and not for everybody else, right?
Yeah, that's true. But I talk about high school, yes. Yes.
Right. concerning mathematics, what are your dreams in that direction? What are the visions in just short words?
Needs to be changed to the extent that we can deal with quantum mechanics. And this, of course, exactly what the people in theoretical physics like to do. But we probably can look at it from our point of view to have a geometry that can cope with quantum mechanics. And this is exactly what Riemann said actually in his famous address. He wants to see a geometry which can deal with very, very tiny region and also very, very large region. Many people did not read Riemann's first paper. And this paper has many, many ideas about space-time, which in many ways already tackle the problem in general relativity. The one of the greatest paper, I think it's better than Curing's paper.
Any dreams?
Yes, my field is algebraic geometry, and it combines algebra and geometry. And algebra is digital, geometry is analog. So I take best part of both. I think algebraic geometry is best for me in that sense.
You? Mathematical dreams?
Yeah, so find solutions to some problems I'm thinking about. And, so maybe I can work in number theory, and number theory it's like an umbrella term for almost anything. So so maybe so I don't know, maybe learning more things. And, so maybe I'm still like learning and searching for the perfect dreams.
Okay. Sorry? Right. Good idea. Are there some questions from the audience to the panel?
Thank you. So I have a simple question. We'd like to ask our panelists. Which special aspects of your research fields attracts you most? Thank you.
Which specific aspect of your research field attracts you most? Maybe I start with an answer. For me, it's the combination of geometry and analysis in physics. When, for example, in general relativity, three things come together: physical intuition, geometric models, and then analysis in order to prove theorems. That's sort of the fascination for me. Some other?
I think I like the structures in representation theory, and also the connections to many other fields. That's the thing which attracts me a lot.
For me, I think it's a simple principle that can give us a deep understanding of some part of mathematics is exciting. That's how I was so excited by the Calabi conjecture. The statement is simple, and it was able to create many interesting universe or space, and that have deep into the nature of geometry. I found that extremely fascinating. That's why actually, when I was a graduate student, I preferred to work on this problem than Riemann process when Chen asked me to look into Riemann process. And I feel that it's far more exciting. Once I got excited on it, I actually put in full time to try to learn it, how to do it. I bring this same thing as to my friend Richard Hamilton when he's strike gold by looking into the rigid flow and then he want to solve every problem by rigid flow. And he succeed to a large extent.
There was some other question also in the audience.
Hi, my question is for Professor Wielzowska and Professor Shan. As female mathematicians, what's the most challenging thing you have in your study and career journey? And what suggestions do you have for female students who like math or will not take it as their career? Thank you.
Yeah, so maybe a difficult thing for me was actually traveling to follow my job. So, but that's probably also difficult for male mathematicians or mathematicians of any gender. But I think that maybe for a woman this is a bit more difficult. And yeah, so I don't know what would be a remedy for that. And I think a very important thing is the support from, at least for me, very important for me was the support from my family, so that my family helped me to go through this journey, not only scientific, but often also very like physical journey through the, from country to country. And just so again, as I told you, I don't know what is the remedy to this, so maybe things have to be like that, but and then of course to for other female mathematicians, what I could say is just to encourage them to follow their dream, to do somehow not to give up, and to believe that at the end everything will be good.
I think, how to say, so there is some biased opinion from maybe more like people outside of math, of thinking like perhaps like males are better for doing math, and females, they have some characters, it's not good, and well, it's not adapted for math. And then I think about this question for some time, and then I came up with this idea. I think it's just, you know, like in some languages, there are words which are masculine and their words are feminine. And when you're doing math, there are certain characters which we can say that, call them masculine characters. Like, I would just do some example like persistent or some strength, or like, you know, it's good for doing math. But there's also some feminine characters, which people think of feminine characters, which like being patient or careful and this kind of things. And I think it's just as human being, everyone, it's better to have more characters. It's better to have both masculine and feminine characters, and that both helps for doing math. So I think girls should be confident on themselves, and if they're interested in math, just go ahead.
Are there other questions? It's over there. Oh, here. It's okay.
Hello, thank you for sharing your dreams with us. I just wondered, with the advent of quantitative finance, do you see the flow of talent away from academia to finance? Is it a thing? Thank you.
Are we losing mathematicians towards
basically.
finance?
I was chairman in Harvard University about 15 years ago. Many of the investment firms in Wall Street called me to try to recruit the students from Harvard in math department to go to financial market, offering a huge amount of money. I refused to help them, and then finally they asked me whether I would go, and they offered me $2 million per year. and I turn it down in the phone. So it depends what your interest is. I don't believe that all exciting mathematicians who are excited by mathematics will go to Wall Street. Only a small number will go, but not all of them. But of course, some of them are extremely successful. Jim Simons was my friend, and he made a tremendous contribution back to the mathematics community, which I admire very much. But Jim Simons always interested in mathematics, even a few years before he died, which I admire very much. But he did make important contribution in mathematics before he went to Wall Street. I don't think financial market or financial investment will make much difference for us. I was told that Gauss was also interested in investing. That's how he created statistics and many different subjects. No problem.
Thank you.
I think we have time for another question. Yes, over there.
Yeah, so I would like to ask, like, when you tackle a difficult problem, how to make yourself motivated and when you get stuck?
Who wants to answer?
So maybe one way I try to, I think I read it in some books. If you find a problem and the problem is very difficult and you get stuck, then maybe it means that the problem is truly challenging. So when you will finally solve it, the regard will be really, really great.
So if I'm given a difficult problem, and if I get interested in, I spend hours and hours. I know a friend of, I know someone who can think any problem, but only up to 1 hour. In my case, I don't mind working hours. But when I found something, I try not to, in the evening, I try not to think further. I take a memo and go to sleep. Because if I kept working on it and found a mistake, I will never be able to go sleep. So that's the best way to keep working.
Thank you very much.
Well, there's a question, what level of stuck that you get into? If the stuck is rather superficial, you can always come back fast and quick. Maybe after an overnight sleep, you can wake up and go overcome that. But when you see how tough the problem is, when you got to a point that you see is hopeless, then you probably need to think about carefully, maybe you're going in the wrong direction. When a problem is solved, you really do not know which side is right or which side is wrong. You have to make a choice whether you should go this direction and go in the opposite direction. And that's what happened to me. After 3 years trying to prove the Calabi conjecture, I got defeated so badly because I tried to give a counterexample, and I worked really hard on it, and then I found out it's hopeless, difficult. And then I asked myself, maybe I go in the wrong direction. And then I go reverse way and succeed after 3 years. But that still takes 3 more years to do. And I learned the similar thing that happens to many outstanding problem solvers. Leonard Carlson tried to solve the Lucene conjecture, and he worked on it for many, many years, maybe more than 15 years. And finally, he found out he got stuck in a very sensitive way. He told me that he found out he should go in the wrong direction, go in the opposite direction, and then he solved the problem. So it really depends on the level of stuckness. if it's serious, that you try all kind of method, you still got stuck, then maybe you are not working in the right direction.
Thank you. And it's getting late, and Professor Yao told us how important it is to have a good night's sleep, and we still have a wonderful performance to expect. And therefore, it's now time to thank you for your interest and to thank the panel for the many interesting discussions. And I think we should, in particular, thank Professor Yao for setting up this evening and let us have this discussion here at the ICBS. Thank you very much.
Thank you for all the professors. Please be seated in the audience and have a rest. Thank you. It's really a deep and profound discussion which inspires us a lot.